Episode 94, A Star is Born. And welcome back for another edition of the Syzygy podcast. My name is Chris Stewart, and I'm sitting in the office of Dr. Emily Brunsden here at the University of York. Hi, Emily. How you doing?
Hello. Very well, thank you.
Good. How's your week been?
Very good. On the final countdown weeks now.
Yeah, it's very exciting. Those of you who haven't tuned in for a while, final countdown weeks to what, I hear you ask? Emily, what's going on?
Till, I guess... Well, you don't go boom, do you, when you give birth?
I sincerely hope not.
But you might go pop.
Yeah. Well, again... Let's hope not. I mean, it's not a sound effect that you want to hear under this. But look, Emily is going to be having a baby soon. Hence, if you look back at the last several episodes of this podcast, you might see a theme. And we're continuing with that theme again today. We started with the baby universe, and then we followed that up with first stars, or baby first stars, and then we went to baby collections of stars, baby galaxies. Now we're on to, well, today we're going to talk about stars again, but not those very first ones, not the ones that we can't actually see, not the ones that we have to sort of make educated guesses about, but baby first or baby stars in the universe like now.
Yeah.
What do star births look like in the modern era? So baby stars now. That's what we're going to be talking about today.
Yeah. Well, it's very interesting. So we've mentioned several times, I think, in the past, we were just having a quick flick through my notebook and having a look at some of the times we've talked about star formation.
Yeah, I mean, I'd be amazed if it hasn't come up in the last 93 episodes. So we must have talked about it, but probably not in great detail.
No. So I think actually just going through from the very beginning, and then we'll have a little bit of a deep dive into some of the more... what happens to a star before it, like, and as it's kind of collapsing, it kind of becomes this sort of pre-main sequence star or proto-star. What happens in those stages before it becomes your sort of normal, as you termed, middle-aged star?
Common or garden variety star. Yeah, so that's what we're going to be talking about today, is stars. Where do they come from? How do they work? All right, Emily, so we probably need to start at the very beginning, yeah?
Yep.
What exists before a star that we can make a star out of?
So we have this wonderful thing called the interstellar medium.
Mm-hmm.
Now, the interstellar medium is kind of what it says on the tin, just in fancy terms. It's the space between stars.
Okay, interstellar,
Yep.
And medium being the stuff that's there.
Yeah. Now, the interstellar medium is really interesting. It's we sort of think about space, and we're actually told quite often that space is empty, that, you know, there's no one to hear you scream, because if you scream, then there's no particles to transfer your sound, etc.
There's nothing in it. That's why it's called space. If it were something in it, it wouldn't be space, would it? It's in the name.
Well, unfortunately, it's not quite true.
Who'd have thought that in astronomy, the naming of something doesn't quite reflect the thing that it is? I'm sure that's come up before. But okay, so if space isn't space, then what is it?
Well, so the interstellar medium is just stuff between stars. Now, it's not much stuff, let's be honest. But every time you've seen a picture of the Milky Way galaxy arcing through the sky, or anytime you've seen a picture of another galaxy with like spiral arms, etc., basically anything that's not a single point of source of light, which is a star, anything that's not a star is kind of stuff that's in the interstellar medium.
Yeah, when you see these amazing, I was about to say photos, I mean, that's not quite the right word, these amazing images of other galaxies and things, or even through like really detailed images of the Milky Way, it's not just pinpricks of light. Like there's other stuff there. There's glowy stuff, kind of Milky Way, milky stuff. So that's the interstellar medium that you're talking about. That's the stuff.
And you can broadly break it down into two different things. There's the stuff that glows, like you just said, which is the gas. Or if you want to be really technical, if you call it plasma, but let's just call it gas.
Sure.
And then every time in your mind that we say gas, you can, if you want to be very
you can just
pedantic,
do that little translation.
you can translate it to plasma. It's what most of it's plasma, not all. Yeah, any case.
Just to be clear, I mean, a plasma is like a gas, except that all the bits are charged.
Yes.
So a gas is atoms all separated apart like we have in the air around us, but a plasma is take all of those bits and then put a lot of energy into it to strip the electrons off, and so you've got negatively charged electrons, positively charged ions, and it's a plasma. It's a gas of charged stuff, which gives it completely different properties. But we'll leave that aside for now.
Yeah.
That's what it is.
Yeah. There is neutral gas as well, but broadly it's mostly plasma. So yeah, but let's just call it gas.
Okay.
And it's glowing because there's photons that are coming from that gas because it's been excited by something, whatever process it's been excited by. So it's emitting photons to get rid of that kind of energy.
Right. Okay. And that's the interstellar medium, as opposed to the like intergalactic medium, which must be much thinner still. There's not a lot of stuff between galaxies. But between stars, there is more stuff. But you said a second ago, there's not much. So, like, what's the density of the interstellar? I kind of feel like we talked about this a little while ago, but just remind us.
Yeah, well, it depends on what you're looking at. So, as we said, we've got the glowy stuff, which is the gas or the plasma. But we've also got the dark stuff, right, which is the dust.
Right.
Or sometimes it's the molecular gas as well. So the dark stuff, let's just say it's mostly the dust, which if you see, again, the picture of the arc of the Milky Way through the sky, all these sort of dark tendrils and things that are going through that.
There's a lot of detail. So what's the difference between dust and, it sounds like a really dumb question, but what's the difference between dust and gas? Is it the size of the bits?
It's actually, it's particulate matter, so it is actually stuff.
Right, so it's chunks of stuff. Like
Yeah.
if you look at it, it's at small enough scale. Put it through a microscope, the gas or the plasma is individual atoms or ions or molecules, whereas dust is like chunks of stuff.
Yeah, and it's like things like silicates, graphites, etc. So
Actual dust.
Yeah, so it's not quite the same as the dust that you sort of have to take off the windowsill every sort of few
Hoover
weeks.
up around the house.
Yeah. It's actually a lot smaller than that. Right. It's you will really need your microscope to get it out.
It's not flakes of skin and bits of pet hair. No.
Yeah, it's about micron size.
Right, okay. That's pretty big compared to an atom or a molecule.
Yeah. So, yeah, cigarette smoke is how I've always heard it sort of described.
Yeah. I mean, that's not a particularly poetic way of thinking about space, but sure, let's go with that.
So we got dust and gas. Now, these sort of constituents of the interstellar medium, actually, they can exist in what we call 4 different phases, or there's 4 different kind of groups of parts of the interstellar medium that you might want to look at. They're not very creatively named. I'll give you the names of the 4 first.
Go on then. Yep.
We've got hot, warm, cold, and interstellar clouds.
Okay, all right. Yeah, I mean, that gives me a sense of what we're talking about, except maybe for the last one. So, right.
Yeah. So I think it's really important to talk about a little bit just all these ones. Otherwise, if we say that stars just form out of the interstellar medium, it kind of gives the impression that they're just forming anywhere and everywhere.
Yeah, they're just there.
But that's not the case at all. They've got to be under these very specific environments. So the first in our categories of the interstellar medium, we've got hot interstellar gas.
Yeah.
Now, it's not a joke, really, that it's hot.
Hot is an understatement, maybe?
Hot is about 1,000,000 Kelvin.
That's pretty warm. Yeah.
So
Which
1,000,000
goes
degrees.
completely against your sense of space, right? Space is space is empty and cold. We all know this. You freeze to death in space if you don't have your spacesuit with you. So how is that possible? How can you have 1,000,000 degrees Kelvin, which for those of you not familiar with the Kelvin scale, it's the same as Celsius, just out by about 294 degrees or something. So on the scale of 1,000,000, it's irrelevant. It's 1,000,000 degrees C, right? So how can you have space at 1,000,000 degrees?
Well, this is just what temperature kind of is. It gets really weird when you talk about the temperatures in space, because temperature is just the speed at which the particles are moving.
Right. So you can have very energetic particles at very high temperature, but not many of them.
Exactly.
Right.
Yeah, so really low density. So if you were to sort of step out into the part of the hot into cloud gas, let's say, then you would still freeze to death, even though it's 1,000,000 degrees.
That's weird.
Because when you experience temperature, what you experience is like particles of air or molecules of air or whatever crashing into your body, right? If there's just none of those crashing into you, or there's very, very few, even if they're going very, 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 very fast when they crash into you, you still radiate all your body temperature away faster.
Isn't that nuts that you can freeze at 1,000,000 degrees? I love it. Okay, so as you say, the hot one is indeed very, very hot.
Yep, very hot and very, very rarefied. So if you talk about atoms, I'm going to use atoms per cubic centimetre because that's kind of a useful
All right,
little
cubic centimetre,
scale.
that's a sugar cube.
Yeah. You've got about 0.005 atoms per cubic centimetre.
Like a tiny fraction of an atom per sugar cube-sized bit of space.
Yeah.
That's basically nothing.
In
There's
fact,
nothing there.
You'd kind of have to go to a giant, 2 kilo bag of sugar, I think, to find one atom.
Find an atom. Okay, yeah, like when we said space was empty, we were pretty close to within a rounding error. There's nothing there.
Yeah.
But what is there, the almost not quite nothing, is really hot. Space is weird.
It's very weird.
Yeah.
And interestingly, this is part of kind of the space that the sun lives in at the moment. We're actually in the middle of a hot intercloud gas bubble.
There you are.
Called the local bubble.
Nice.
It's fascinating because it's nothing to do with us at all.
Right, we just happen to be in it.
We just happen to be right bang smack in the middle of it.
So why?
Well, the bubble we think was formed by a whole bunch of supernovae. And actually the sun's just kind of wandered in.
So we're just drifting through it. It's not going along with us. We haven't sort of picked it up. We're just wandering through it at this point.
Yeah.
Right.
So it's quite
Cool.
cool.
There you are. I mean, I don't know what that means other than, interesting fact. I'll pull that one out at the next party I'm at.
Yeah. Then we have the warm intercloud gas. Now we're just going to come down in scales now.
So hot is 1 million.
Yep.
Warm could be literally anything from sort of 0 to 1 million at this point. So, okay.
Do you want to take a stab?
I don't know, Emily, like 10,000 Kelvin.
It's pretty good. About 8,000. Yeah.
All right. Okay. Yeah. Point to me.
Yep. And then you're looking at kind of between 0.01 and 1 atom per sugar cube for that.
Okay, so that's more atoms, more tiny fractions of an atom per sugar cube, but considerably cooler. But at the same time, can we just take a pause here for a moment to acknowledge that warm is still a couple of times hotter than the surface of the sun?
Yeah.
Yeah. So this is a very different kind of temperature scale that we're dealing with here. Right, fine. So that's warm.
Yep. Well, then we have cold.
Cold.
So cold is about 100 Kelvin. So that's actually really cold for us.
Yeah, like you would, no question there. That's pretty chilly.
Like minus 100 and whatever degrees, right?
Yeah.
So, yeah.
That's colder than you're going to find anywhere on Earth.
And then, so you're looking at between 1 and 100 atoms in your sugar cube for that.
Okay, so that's actual atoms you could find there in your sugar cube bit of space.
Mm-hmm.
More atoms, but they're colder. And those things go hand in hand, right? The more you heat up the atoms as they're bouncing around against each other, the more energy they've got, the more they're going to tend to fling each other apart. Like those things tend to go hand in hand in temperature.
Yeah.
Is the hotter you are, the more you tend to expand, the more spread out you tend to become.
Exactly.
Yeah.
And actually the first two, the hot and the warm phases of the interstellar medium, they're actually ionized. So the atoms are actually not atoms. They're split up to their nuclei and their free-floating electrons.
Right. So they are plasma. Definitely plasma. Yeah. But down in the cold one...
Cold one's kind of a bit more neutral.
Yeah.
By this point. Now, it turns out that all those three are utterly useless when it comes to forming stars.
Right. So we can just ignore those now.
Yeah.
Okay, good.
I mean, it's good to know they exist.
Yeah.
But,
for completeness.
Yeah. So we actually come to the rarest category of the interstellar medium, which we call interstellar clouds.
Interstellar clouds. And what's their temperature on this ridiculous scale?
Well, quite cold. We're talking around about 10 Kelvin.
Okay. So we are continuing. So they ran out of descriptors. We went hot, sort of medium cold, super cold, uber cold. No, we're calling them clouds.
Yeah.
Why change all of a sudden? Why couldn't that have been the cold?
Well, freezing. I
don't know.
But they tend to be more, I guess, they're smaller in scale. So whereas like something like the local bubble, which it sounds like a sort of a little balloon that we're sort of, I don't know, transiting through. It's actually really huge. It's kind of 700 light years or something across.
Yeah, okay, that's fairly large.
It's these large clouds are, and the warm and the hot, etc. They're big scale, whereas these little clouds are quite localized, quite small comparatively.
Okay, so hence the name cloud. It's sort of a little dusting of this stuff across the sky of the cosmos. Yeah.
Yeah. And so we're now up to something like 100 to 1,000 atoms per cubic centimeter.
Right, that's quite a lot indeed.
It's still not lots, but
compared to the hot one, which was a tiny, tiny fraction of a percent, It's quite a lot.
But we're now at the point we're cold enough that actually we can start to not just have neutral gas hanging around, but we can actually even have molecules.
Right. So they're close enough and they're cold enough that they could actually join.
Yeah.
Okay.
So now you need molecules and this kind of density to start off star formation, because star formation and actually stars throughout their entire lives are just kind of tippy scales in terms of balance between gravity and pressure.
Right.
And you need to have this kind of density in order for gravity to start to actually have a finger in the game here.
Right. Gravity's got to start taking over and drawing things together to start turning it from a spread out gassy thing into more of a clumpy thing that could become a star.
Yeah.
And you need molecules for that, not just atoms.
Exactly. Yeah. So you need those gravitational forces to be, well, between more massive things, and also to be only acting over shorter distances. So forget about the hot, warm, cold ISM that's just not going to collapse into stars. You just need these little clouds of the very, very cold, the interstellar clouds.
That's really cool. I mean, it's a lovely transition, because normally when you talk about atoms or even molecules, gravity is utterly irrelevant. You know, they're so small and gravity is so weak that it just never comes up in the conversation. It's utterly irrelevant. But here is an example where not only, we're talking about a gas on large scales. It's not on the scale of individual atoms or molecules. But you have to have the molecules. You've got to have chunks that are big enough for gravity to be able to just subtly start taking over. I think that's really cool.
And these chunks are really, really rare. So we're talking about maybe 0.1% of interstellar space is kind of in these kind of very, very dense, cool clouds. So it's not much.
It's not a lot.
But the good news is that these molecules, etc., will start to help us form stars. Mm-hmm. And this is where we come to quite a big difference between the stars that we talked about 2 episodes ago and the stars that we actually see forming around us in the universe, or in the Milky Way galaxy today.
So when we talked about those the very first stars, they were a bit crazy, weren't they? Because they were forming out of the only stuff that existed at the time, which was hydrogen and helium and nothing else.
Well, yeah.
Maybe a tiny little bit of lithium or something.
Yeah.
But it's basically
pretty
hydrogen
much
and helium.
Those two.
And that's a bit weird.
Yeah.
At least in the modern era, stars are much more complicated.
Yeah, so really molecule-wise, and for the first stars, you really only had molecular hydrogen, which is still, not that much to form out of.
Yeah.
Whereas today, we've still got molecular hydrogen, but we've got things like methanol, we've got acetone, we've got carbon monoxide. So lots of, basically, just when you look at the formulas for these things, it's just different ways of sticking hydrogen, carbon and oxygen together.
Yeah.
Right?
And presumably other things around the same kind of like a bit of nitrogen in there and so on. But yeah, you've got these not huge, like carbon and oxygen aren't enormous atoms. What carbon's got, six protons and electrons? Is that right?
Yeah, it's carbon 16, isn't it? The full mass.
And oxygen's got like 8 or something. So they're not enormous atoms, but they are, bigger and more complex than hydrogen. And there's a lot of that kicking around at this point because of all the previous cycles of birth and death of stars previously that have just kicked it all out into space. That's where all of this has come from.
Yeah, so it doesn't take a lot of these kind of significantly heavier than hydrogen molecules to start to come together to get a lot more gravitational attraction between them.
Cool.
So that's your ingredients list, I guess, of what you need in order to form your stars.
How to make a stellar baby. Just get a bit of, what do we call it? An interstellar cloud?
Yep.
Interstellar cloud filled with a bunch of different atoms and molecules and add gravity.
Yeah.
Yeah.
And you can have a bit of sprinkling of dust in there if you want as well. That's fine. You're allowed that.
Just for flavour.
Yeah. So that's your ingredients. And then you can start, I guess, the gestation.
Mm-hmm.
So you got to start off small. You start with these gravitational interactions between individual molecules that then start to come together, stick together. And because this cloud is very cold, it doesn't have the opposing force to kind of stop things sticking together with gravity. So an opposing force would come from pressure, which generally is related to temperature in these clouds. So the higher temperature, the higher pressure, because the atoms are moving very quickly. These atoms are at 10 Kelvin. They're not going anywhere.
Right, okay. So, I mean, when they're at high energies, if they do come together, that's bashing together, there'll be a big exchange of energy. They'll bounce off again, right? As you might expect. Boing, off they go because they've got lots of energy. But if they're very cold, they might just sort of bump against each other, and maybe other things will say, "Oh, you're quite close to me now. I'll stick around." And that can take over at cold temperatures where it wouldn't at high temperatures.
Yeah, so you get this kind of collapse happen. Now, these clouds are sort of fairly large. They're depending on whether you want to be a molecular cloud, it's called, or a giant molecular cloud. So a molecular cloud will be kind of 1,000 times the mass of the sun. A giant molecular cloud, maybe 100,000.
Okay. So it's just a matter of scale there, but it's the same stuff.
Big molecular cloud or small molecular cloud, it will clump down into these smaller parts, right? So you don't get sort of one enormous cloud collapsing all at the same time. You get parts of that cloud which were just randomly a bit more dense than the others, and those little parts start to sort of clump down into what will eventually become stars.
Okay.
And that's where we start coming into the realm of the proto-star.
All right. So we've begun. We've got our ingredients. Gravity's taking over, and it's collapsing down in these particular regions, which just, there's no rhyme or reason for it. It's just, it happens to be a bit denser there, and that just takes over and goes out of control. Great. So what then defines proto-star as opposed to that region's just a bit more dense?
Yeah, well, we do actually have a reasonably sensible definition, actually.
Good. I like it when definitions make sense.
I mean, no definition's ever sort of concrete and solid in astronomy. But
you can't ask too much, but let's go. What have we got?
So we actually want our core to be about 1 million Kelvin of this clump.
Okay, so as it's collapsing down, gravity is pulling things closer together, and that's increasing the temperature because there's a force acting on it, which is pulling everything in, but that means that they're going to be bashing against each other more and more and more. And as you're constricting it into a smaller space, the temperature is rising.
Yeah.
Yeah.
Or if you like to work in energies, you can say that the gravitational potential energy is being converted to thermal energy.
Right. Same principle as when you're pumping up a bike tyre and squeezing more and more air into your bike tyre. The tyre gets hot because you're squeezing relatively cool air into a small space. You're adding energy by pumping it in, and that energy is showing up as heat in this high pressure environment. Okay.
Yeah. So, and the core of this sort of little region that's collapsing is always going to be the hottest bit because that's the densest bit.
Right. Okay.
So it's more like you're sort of piling sort of stuff into that core, contracting it and then making it hotter.
So it warms up and we get to what temperature?
1 million Kelvin.
1 million Kelvin. Wasn't that the temperature that we said before was the hot interstellar medium? Yeah, okay.
Except now we're not talking about sort of a few atoms whizzing around at 1 million Kelvin.
No, now we're talking the core of a collapsing protostar. Cool,
Yeah.
and that's when we're allowed to call it a protostar.
That's when we're allowed to call it a protostar.
Okay.
And the interesting thing is fusion starts now, which you might just say, hang on, we just started fusion. That's just a star. Now, it's...
Isn't that a star?
Yeah.
Can't we call that a star?
Well, we can't because it's actually not hydrogen fusion as we know it.
Right. What is it then?
It's deuterium fusion.
Okay, deuterium is heavy hydrogen.
Yeah.
Right? Hydrogen comes in several different forms. Normal, everyday, common or garden variety hydrogen is one proton in the nucleus and one electron whizzing around the outside. Hydrogen's always got one proton. That's what makes it hydrogen and not something else. But it can have one or two neutrons with it as well. So hydrogen is one proton. Deuterium, proton and neutron.
Yep.
Tritium, proton, neutron, neutron.
Yep.
Yep. Okay. So we've got some deuterium kicking around.
Yep. And that deuterium plus an ordinary hydrogen. So we're talking about nuclei. I mean, the electrons are they're too hot. They've gone.
Right. Yeah.
They're off doing their own thing.
They've whizzed off. Yeah. It's not important.
So if you put those two together, then you actually get helium-3.
And does that one kick in first because that's just the easiest nuclear reaction to do?
It happens at the lowest temperatures.
Right.
Yeah.
Right.
Yeah. So you've gone from, I think, what do we got? We got two protons coming together with one neutron, which goes to helium because you've got two protons there, and then helium's got one neutron.
Yeah. Yeah, well, often helium has 2 neutrons, but in this case, you've only got the one to go
Yeah.
with. So, yeah.
So it's called helium-3 because helium-4 is kind of the normal one, and we've just removed one of the neutrons to make it 3. It's all numbers.
Yeah,
game,
it's just keeping track of things.
And I'm sure I can do chemistry sometimes, right?
I'm sure you could. But we're not allowed to call this a star yet because we're not burning hydrogen. And is that like, as in hydrogen, single proton hydrogen, normal hydrogen? So is that a definition of a star, or is it just simply because there's not terribly much deuterium around, and so we can't rely on that long term? Like,
it doesn't keep it going. It's not a star per se. But yeah, exactly, you're right. You need to have this traditional, normal hydrogen fusion to helium to become a real star, to sit on the main sequence, we call it, to go through millions, billions of years of life.
Okay, it's got to be using, because it's going to have a lot of hydrogen to burn in that way, to fuse in that way, and it's sort of self-sustaining in that way. Whereas you couldn't say the same if it was just trying to do deuterium.
No,
that'd be over very quickly.
Yeah, it does happen around for a little while, but it's very ad hoc and kind of just yeah.
All right, so proto-star. It's doing starry things, but we're not there yet.
No, but this is when we have the first surface, if you like, would appear for our star.
Okay.
So I mentioned this was a core, so that the kind of the core of that collapsing cloud. So when you've got deuterium fusion happening, then that kind of tells you what the surface would be. And in what we call the photosphere, actually, which is where photons would come from a star. Now, it wouldn't look much like a star that we'd be familiar with, I guess, just looking at today, because it's about, probably a few thousand times bigger than, say, the sun.
Wow.
Surface.
Okay. Yeah.
It's big. I mean, it's still collapsing, right? It's still going through that process.
Yeah, it's funny. In my mind's eye, I'm imagining this as a fairly small thing, but of course, it's spread out over such a huge scale, and then it collapses down. That's what collapsing down means. So, yeah, it's over huge scales. Okay.
And this deuterium fusion is actually quite efficient, which means it's actually thousands of times more luminous than, say, the main sequence star that it will become one
Efficient
day.
In the sense of churning out energy.
Yeah.
It's giving out a lot of photons.
Okay. Yep. So huge, enormous
and
stuff.
Bright.
Yeah, very, very bright. Now, the absolute paradox of this, of course, is that we can't really see these stars.
Sorry. They're really big. You just said they're really big and they're really bright. Yeah?
Yeah.
But we can't see them. Astronomy makes no sense. Why? Why can't we see them?
Well, there are 2 reasons. The less important reason, but I'm just going to say it anyway, is the fact that actually most of the light's coming out of the infrared part of the spectrum.
Right. So we literally can't see them with our eyes. Sure.
But that doesn't matter anymore. Modern day astronomers have infrared telescopes.
We have tools to do this for us.
Yeah. It's fine. But actually, the most sort of hindrance that we have to seeing these things is that they're still buried really, really deep in these enormous molecular clouds that are blocking all that light from reaching us.
Right. And infrared is blocked really well by dust. Do I remember that correctly?
Yeah, it depends on the temperatures,
right.
but basically you've got the dust and gas that's just all in the way, absorbing all the photons that are coming off the star.
Right. All that structure that you can see on a really clear night of the Milky Way, all that dust and stuff is actually blocking the view of the really bright central part of the Milky Way, right? It's blocking out all that light. And so that's exactly what's happening here. So what you're saying is we could see them if it weren't for the fact that they're forming in areas where there's actually going to be a lot of dust.
Yeah.
And so we can't see them, but we could see them.
Yeah.
Right, that makes much more sense. Okay.
Sure. Well, and we have got some examples of later stages of proto-stars that we have been able to see with some infrared telescopes. Depending on what infrared part of the spectrum you're using, you can sort of peer through a little bit of this dust and gas and sort of see some of them, but mostly in the later stages of their evolution. So, yes, but the collapse sort of mechanism is still going on. And it's just continuing, right? So the star's not just going to sort of stop there and just sort of hang out and say, now I'm a big protostar. What are you going to do about it? So you've got this continual collapse, continual shrinking, continually heating core.
Because that process continues. Like the collapsing down continues because gravity is always attractive, as far as we know. And so that's going to keep contracting down at least until something balances it the other way, something pushing outwards. And we haven't reached that point yet.
No.
Okay.
What's really cool, though, as this whole contraction process is going on, I think this is one of the surprising things, I think, about stellar evolution. I always find myself surprised when I come back and read about it, even though I've known it for a long time, is actually whilst the collapses happen, so the star's getting smaller, this core is getting hotter and hotter and hotter, but the actual surface of this protostar basically stays at the same temperature.
That feels very counterintuitive to me. How
Weird,
does
isn't
that
it?
work?
It's a very cool little piece of astrochemistry, let's call it, where you actually have a thermostat on the surface of your star regulating the temperature. And the little thermostat, the little sort of ion that's doing this is actually H- or negative hydrogen.
What?
Yeah.
H-? What's that?
Hydrogen with an extra electron.
Oh, I didn't even know you could do that. That's not something you normally come across with hydrogen. Hydrogen is normally proton and electron. And if you do anything with the electrons, you rip it off, right? And it just becomes a proton. It's a hydrogen nucleus. It's just a proton. So H+. But you can add another electron to an atom to make a different kind of ion, make a negative ion. And sometimes that's the thing that the atom wants to do, because electrons often want to make pairs when they're around atoms. And so if your atom doesn't normally have a pair of electrons where it likes to have a pair of electrons, and it can just whip in another electron and form a negative ion with an extra electron. You never hear about that with hydrogen.
Well,
that's weird.
It only happens under like certain conditions, certain temperatures and pressures. So it doesn't happen kind of in the laboratory around us today. Yeah. But so this H- ion that you've got sort of kicking around, what happens is that controls the temperature. So if the star's surface starts to get a little bit too hot, then the whole thing becomes rarefied, and actually your H- starts to disappear.
Right.
And so then when it becomes rarefied, the energy can escape really efficiently, and so the whole surface cools down, and then it kind of collapses back down to its original size, original temperature. If you go the other way, if you get a bit too cold, then you get too much H- being produced, then you get kind of the opposite effect. So then it starts blocking the energy from escaping from the star. So the star starts to heat up, then it comes back up to its...
expands out. And
yeah.
That's crazy. That may well be the first time I've ever heard of H- being a thing that does something. I'm sure any chemist listening to this is now yelling at me going, no, Chris, there's all these other applications. But that's wild. I've never heard that. That's crazy.
I do need to go check now because you've now got me really confused. I was sure it was H- with two electrons.
That sounds plausible.
It's not just electrons themselves. Can't be just electrons themselves.
Listen, if Emily's got that completely wrong, look, it still makes a great story. And you can email us and tell us. That'll be fun.
The thermostat's there anyway. So
Sure.
It sits there and does that.
Yeah. And let's say,
which is
for the
really
sake
cool.
of an argument, it is H- doing a thing.
Yeah. But the point is, that's really cool. The star's surface temperature doesn't change, but the interior, of course, is just heating up and more and more and more and more.
That's crazy.
Cool, huh?
Yeah. Love it. All right. So we're collapsing down.
Yep.
And keeping the surface temperature bizarrely the same as we go down. But the core is getting hotter and hotter and hotter.
Yep.
Which means, presumably, we're getting closer and closer to being able to fuse other stuff than just the deuterium and the hydrogen.
Yeah. Now, we've got a few little steps to go along the way to get there first. The first thing you might want to ask, well, what if you don't have enough mass? What if you'd never get hot enough to do anything else interesting in terms of
so
being
the collapse could still continue, but it's just there's not enough stuff there. The temperature's increasing, but it's just not enough, right? It's like a car trying to turn over, trying to start the engine, and it's just not getting there. So what does happen?
This is the origin of our brown dwarf stars, or failed stars.
So brown dwarf is already a bit sort of wonk wonk. You didn't quite get there, but it's better than failed. Failed is just depressing. I'm a brown star. It was better than a failed star.
So you need to be a brown dwarf, then you need to have less than, I think it's 0.08 solar masses. If you've got more than that, then you're going to be fine. You're going to become your star on the main sequence, and everything's going to be fine.
But that's fairly close, right? That's not too far off the mass of our sun.
0.08.
Oh, 0.08, sorry.
Yeah, so 8%.
Right. Yeah, it's quite a lot smaller then.
Yeah. So, quite a lot smaller. But, so if you don't have that, then you're just never going to get the temperatures that you need to have hydrogen fusion. You're never going to be a star.
It's not going to happen. Game over. Sorry.
But as long as you've got more than 13 times the mass of Jupiter, then you're still at least a kind of a star. This brown dwarf.
Yeah, all right. So below that, you're not even getting the color. You're not even we're not even playing this game.
You basically
but above
just
that was all right. We'll give you the bronze award, the brown award, right? Which is you're kind of a star. Well done, congratulations. It's like at the sports carnival at school where you get the participation award. Thanks for coming. Yeah.
I mean, it did try to do fusion. It got things got
warm.
warm.
Gave it a red hot go. Well done.
Yeah.
Better luck next time. Yeah.
And they're warm enough and bright enough that we can find examples of brown dwarf stars, and there's various classes and so on.
Right. So you can actually see them. I mean, they're right.
We've
so
got a few that we know of.
They're hot enough to see.
Yeah.
Okay. It's just a shame they had to go with brown. Like I kind of feel like even grey. Like grey's kind of a bit stylish. Could have been a grey star, but a brown. Do I have to be brown?
Well, we also, we've got to be careful because we've got white dwarfs and black dwarfs, which are also completely different things.
Yeah, okay. So grey would sort of imply that it's up there in the similar category, somewhere in between.
Possibly.
But no. This is brown. This is sort of, I guess you could have gone with khaki or something, just.
Yeah. But anyway, but they've got usually, they have to have more than 13 times the mass of Jupiter. This is an official IAU definition, actually, that you need, once you're 13 times the mass of Jupiter, you're no longer a planet.
Right.
This came out of the other, from the other direction when we were finding these enormous Jupiter size.
When is it a planet and when is it not a planet? Yeah.
So that's where the 13 comes from. It's kind of a fairly arbitrary number.
Sure.
But, so you're not a planet anymore if you're 13 times the mass of Jupiter.
Right. But you could be 12 times the mass of Jupiter and still have a little bit of fusion going on.
You can, yeah.
But we're just officially going, no, look, I'm sorry. Just stop. Just stop. You're a planet.
Yeah.
Give up.
Basically.
Yeah, okay.
Anyway, so that's the origin of those parts. But let's go with the scenario that you have got more than...
Sure.
Let's say 0.08 times the mass of the sun.
More than 35 minutes into the podcast. Let's actually get to stars. Okay, yeah.
Well, we're only going to get proper stars at the end of the podcast. I hate to be a spoiler here.
Fair enough, yeah.
But anyway, so I guess you could almost call proto-stars this kind of gestational period because there's an event which is a little bit like a birth, I guess, when it can happen with you've got your stars and you can have your... even though you're not a fully fledged, full hydrogen fusing star, you can have what I think is probably analogous to a birth by the point where you start to switch on something called the proto-stellar wind.
Proto-stellar wind. So we've got a proto-star, now we've got proto-stellar wind.
Yes.
In terms of our analogy to actual human babies, the wind normally happens after the birth. But okay, we'll go with this.
Yeah, I mean, it's not particularly like a wind in terms of a gentle breeze, let's say. I mean, this is something...
Mind you, neither is a baby's wind, but you'll find that out. That's a surprise for you.
Protostellar winds are pretty nasty.
Yeah.
So they're kind of these enormous... so we have the solar wind that we've mentioned several times with Parker and so on. It's this kind of outflow from the surface of the sun of particles, charge, etc. That's then, blasting through the solar system.
Yeah.
Kind of that, but like a million
But
times
on
stronger.
steroids.
Yeah, so you've got this
Why is
huge...
it so violent? What's going on? I mean, in my mind's eye, I'm imagining something which is not yet, hasn't formed a star yet. It's very big. He says very big. It's very bright, even though we can't see it. But I don't imagine something which is really violent yet. It's still collapsing down. Where is this all coming from?
Well, we need to zoom out a little bit in terms of our point of view, because we've been talking about the surface of these protostars. We actually haven't been looking at what is beyond that surface.
Right.
And beyond that surface, we've still got an enormous disk of material from the collapse that's still kicking around, contributing mass to the protostar. We've also got, at least in many, many cases, an enormous bipolar outflow.
Ooh, it sounds cool, but I don't know what that is. What is that?
Jets.
Right. But why? Why are you getting jets?
Well, so you've got anything time you've got a disk and you've got infall material onto that disk, if you throw at least a couple of other kind of bits of physics in there, some magnetism, for example.
Magnetism messes everything up.
Yeah, it's really hard.
Yeah.
But anyway, you end up with these two jets which are pointing perpendicular to the disk from the top and the bottom of the star.
Right. So this is, you've got to imagine a whole bunch of gas and dust, which then starts swirling because we're collapsing down, and any bit of rotation gets faster and faster and faster. It's the whole ice skater thing. You start pulling your arms in as an ice skater, you go faster and faster. But that means that you've got all of this stuff, a lot of which is charged. Anytime you've got charged stuff whizzing around, you get magnetic fields. And the faster you go, the bigger the magnetic fields. And those magnetic fields will be perpendicular, along the pole of the direction of spin. And so what does that do?
It sort of throws up material, that the infalling material gets caught up in all these magnetic fields. It's a little bit like a dynamo. We don't actually understand the full set of physics behind it. So it's not just me being vague because I didn't bother reading about it.
Come on, Emily.
There is quite a lot of really physics that goes into this that we're still not quite sure of.
I've spoken to a few astronomical people who deal in magnetic fields, and they just look confused all the time. It's really hard stuff.
Yeah. But the output is that you get these two jets coming out, which are throwing out material and radiation back into the environment of the star.
And this is a common thing for anything which is spinning like that, presumably on all sorts of scales. But I mean, you hear about them with things like, neutron stars and stuff like that, which are very, very compact, very rapidly spinning, very big magnetic fields that are shooting these sort of jets off, and we get things like pulsars and stuff. But it's even happening at this scale with proto-stars.
Happens with black holes, whether you're talking about black holes the sizes of stars or black holes the size of billions of stars in a sort of the middle of a galaxy. So there's lots of examples of these very extreme sort of environments. But yeah, this is just the one that little baby stars have.
Right. And so this would be maybe the baby star having a good old kick, really kicking away there inside before it's born, but getting a bit angry anyway.
Yeah, definitely. Yeah. So these jets, it seems to be quite a variety of these types of jets. But remember that when we talk about these proto-stars and even the following pre-main sequence stars we're going to get into, we actually don't have a huge sample of them that we can observe. And the reason is not for lack of trying, again.
Right. And it's not because they're not out there. I mean, there must be enormous numbers of these things because we know that there's a lot of stars happening all over the place. It's that you can't see them.
Yeah, well, so it's a bit of both. So you can't see them, but also they're kind of very short-lived.
Oh, okay.
So you don't have a lot of time to catch them in terms of astronomical time. Stars that live for billions and billions of years, well, hey, we're going to see loads of them because they're just hanging out doing their thing for billions of years.
Sure.
Whereas these, we're talking about maybe tens of thousands to up to 1 million years of the star's early lifetime.
Which is not a lot in billions of years.
It's not a lot. Yeah. So if you took like 100 random stars of random ages, then you're only going to have maybe one that's in this
if you're lucky.
Yeah.
If you're lucky. Because that, really as a fraction of lifespan, is not even 1%.
No.
So you'd be lucky to even find one.
Yeah, you probably have to go to like 1 million stars, actually.
Right. Yeah, okay. I can see how that would be a problem. Yeah.
So we have some examples of these. But anyway, for the jets, some of them seem to be kind of slow and a little bit disorderly, the jets. So maybe those stars are just...
bit of a lazy kick.
Yeah, the chilly out ones. And some of them are very much the opposite of that.
Right.
And they're very, very violent. They might have jets coming out hundreds of kilometres per second, lighting up the whole region around them in these quite stunning objects.
So is that where, when you see these amazing images from your Hubbles and so on, of these nebulae which are just glowing in the most amazing ways. Is that what that is? Is that what
it's all part of it? Yeah. So you can see the jets. They're called, and these jets which have little knots in them as well, are called Herbig-Haro objects.
That's a good name. Yeah.
Yeah, well, you can guess who they were named after. But so you can see, and they also seem to be embedded in these reflection nebulae, which means that all the energy that's coming off the star is going into the surrounding stuff that didn't make it into the star, causing it to glow and be really pretty as well.
Are there any like classic examples of this? What should I put as the chapter art here?
There are some. I didn't write down the names of any of them. They're not like the best names, I'll give you that.
Okay.
But yeah, we'll find a couple and put them in the pictures.
Have a look at your podcast player right now if you've got the ability.
Yeah. So you got these jets and so on. Now this is all part of the protostellar wind as well. Basically, these things are getting sort of kind of a little bit uppity, a little bit violent at this point. And then they start their full-on protostellar wind. Then that's when they start to really blow away all the material that hasn't fallen into the disk or into the star itself at this point.
And how is that happening? I mean, what you've described is jets, which are sort of going, I'm imagining sort of, north and south pole. But how are you getting it blowing away stuff around the star as well?
Well, it's kind of, again, it's all linked to the magnetic fields.
Right.
It's a similar situation with the sun. The sun's outputting these particle winds in all directions all at once as well. So,
right. So the magnetic fields are just so nuts that we're not talking polar anymore. It's everywhere.
Oh, yeah.
We're just going to really mess you up.
I mean, you do have a polar, sort of preferential part of it.
Sure.
But yeah, it's all a bit of a mess.
We're not fussed. We're going to go everywhere. Yeah.
So you've got these big particle winds of stuff being blown off the surface of the star. That starts clearing out the region in which it was living in. So whilst your protostars were sort of firmly embedded in these very difficult to see regions, this is why I call it the birth, because in a sense this is where the star emerges from this cocoon of gas and dust, and you can actually see it.
How does it make you feel about what's about to happen to you? It's not a good analogy.
Well, to be fair, what I'm going to go through is hopefully a lot less energetic.
Well, we'll see. Yeah.
Yeah, hopefully there's not so many violent stellar wind events.
Or indeed magnetic fields, I think.
Yeah, we won't have to account for them.
No, one hopes. Yeah.
It'd be a long sum, wouldn't it? So this is the point at which the star becomes a pre-main sequence star.
So we're a star now.
Well, pre-main sequence star.
Okay, but I mean, that's a star.
Well, so was a protostar.
Well, true. Okay, fair enough. So pre-main sequence. So there's a couple of things we need to talk about here. One is main sequence. I think we've touched on how we classify stars in the past, but I think it was a long time ago. And then we need to get to if it's pre-main sequence, then what does that mean? Yeah,
so the main sequence is the time that the star spends during its normal middle ages. It's normal. That's from the time that it first kicks off starting doing hydrogen to helium fusion all the way through to the end of its life, basically when it stops doing hydrogen to helium fusion.
Okay, so that's like the stars, it's finished school, it's gone and got a job, it's settled down a bit, it's got hobbies that it likes to do on the weekend. It's just having a life, right? It's getting on and it's doing its thing, and that's main sequence.
Yeah.
But pre-main sequence.
Yeah, so that's kind of its normal lifetime. It's going to last for a few billion years. In the case of the sun, maybe 10 billion years. But pre is kind of just the last little few steps that it needs to take to get to that point.
Okay, so we're going to talk in this particular episode as the star's well and truly there when it reaches main sequence.
Yep.
Okay, so what has it got to do to get there?
So it's still got to contract and heat up. It's still got to get to a core temperature. So our switch on is at 10 million Kelvin.
10 million Kelvin. And switch on of what?
Hydrogen fusion.
Right.
So
and that's what we're aiming for.
You're a star. You're on your own.
Well done.
Yeah.
Well done. You're fusing hydrogen.
You got your little box, your suitcase. You're out in the world, right?
Right. And so you need really high temperatures, 10 million to do that.
Yeah.
But that process, that fusion process of hydrogen and hydrogen, puts out a lot of energy as well. And once you're doing that, once you reach that point, then that can keep going? That's the idea?
Yeah, exactly. It'll be on its way and you don't have to worry about it anymore. As you say, it's got its job. It's settling down. It's mowing the lawn on the Sunday afternoon. It's fine. But okay, so we've got a little bit of time. Now, the interesting thing about these pre-main sequence stars is that in terms of all of the timescales that we've talked about from day zero, when this cloud had a very tiny slight overdensity in one little place, all the way to the day that it starts hydrogen fusion. The next stage we're going to talk about actually only accounts for about 1% of that time.
Right.
It's going to happen very quickly, but it's really, really important.
Yep. So it's fast, but it's really big. Okay.
Yeah. And actually, these are two of the sort of classifications of stars that I've always been a little bit fascinated with, but never had a chance to really learn a lot about. And then trying to dive into them, maybe that's because we don't have so many of them to study, actually, because they're really, really short-lived.
Yeah. I mean, as we were talking about before, you haven't got a lot of opportunity to catch these.
No.
Yeah.
So, there are two classifications here. We have T Tauri stars and Herbig Beae stars.
Great names. Okay. T Tauri
Yeah.
and the other one.
Yep. Herbig, B-E-A-E. We can just call them Herbigs.
Herbigs.
Yeah,
Yep.
for sure.
Herbies.
And the only distinction between them is, well, the main distinction between them is actually mass. So if you are about, well, less than 2 solar masses in terms of your proto-star up to this point, which means you're going to form a star that's kind of similar to the sun, or even a little bit bigger, a little bit smaller, but around
there.
Then you're a T Tauri star. And if you're bigger than that, if you're up to 8 times the mass of the sun, then you become a Herbig star.
Okay.
If you're bigger than 8 times the mass of the sun, you skip this phase altogether and just go straight.
Right. Okay. You're really big. It's like, no, forget it. Just carry on. Do your thing. Yeah.
Because the bigger mass you have, the faster the contraction happens. And so when you're really big,
skip this step.
You just skip
Right.
it.
Okay. So if you're not that big, T Tauri stars, what happens?
Well, these are the nasty little critters of the universe, I think. If there's anything, I think, that's maybe more misleading in astronomy, at least in terms of nomenclature and so on, then maybe we need to investigate that.
Sure.
But we've talked about how stars are born in stellar nurseries, which is just another term for these kind of active areas of star formation.
Sounds nice.
Yeah, you've just got...
I'm imagining pastel colours and shiny things hanging from the ceiling.
Yeah, and then these little baby stars start to come along, and it's all very cute.
They're lying on their backs on the mats, gurgling away.
These are some of the nastiest objects that you can come across in stellar physics.
Do you know, I think I've been to that nursery, actually.
They're horrible. I mean, okay. So first of all, they're very, very active, which means that the surfaces are changing all the time. Now, if our sun was very active, we would not be around today, right? Yeah. We talked about our sun, and it is active. We've got big things that happen. We've got flares, we've got coronal mass ejections, we've got jets popping up. That's, all sorts of scary things happen.
And if a big one of those came our way, it would be very nasty indeed.
Yeah, and that's our sun. And our sun is like the calm.
Honestly. Just the sun having a tanty once in a while. But this is...
active. And then they're also very variable as well.
Right.
So now these stars will rotate probably around twice as fast as the sun. Mm-hmm. So that tells you something again about the magnetic fields, because the faster you're rotating, the faster you're pulling around all your charges, it's just going to get very, very messy very quickly. They've got huge amounts of X-ray emissions coming off them, very high energies, huge amounts of radio emissions, and radio emissions are often a proxy, again, although radio photons themselves are not high energy, they're pretty much a proxy for something nasty going on.
If there's a lot of radio photons coming off, then there's something serious happening.
Yep. So we're talking about maybe 1,000 times more radio emission than, say, the sun has.
Okay.
So it's
quite a lot.
It's a lot.
Yeah.
You got huge particle winds, protostellar winds. So these are continuing on. You've got huge spots coming across the surface of the star. So
which is what? What is a spot? What is that?
So they're active regions. If you think about sunspot, right? They're usually quite tiny in terms of the surface of the sun, but all it is it's a darker patch that's on the surface of the star that comes from the fact that is a very slightly cooler area. Mm-hmm. That's caused by magnetic field basically pushing material down into the surface.
So it's sort of magnetic fields and convection and stuff like that.
Yeah.
And it's right.
And it's not much cooler than the rest of the surface, but it looks a lot cooler. So you get this kind of silhouetted spot. So you might see sunspots. If you're very lucky, we get naked eye size sunspots, which... Don't look at the sun.
Yes. When we say naked eye, that's not what we mean.
If you use a proper solar telescope or a proper solar filter to protect your eyes, then occasionally we get a spot that's big enough to see. I've seen one.
Yeah, but normally they're much smaller.
Yeah, you just can't see them.
Yeah.
These things are massive.
Right, which is an indication that the surface is in turmoil. There's a lot going on.
You've got flares, you've got these winds. It's just horrible. It's just a nasty little piece of work.
I'm getting a picture here.
Yeah. So it's quite interesting because actually and they can, although we say they're very short-lived, this, depending on how massive the star is, if they're a low mass star, even kind of 1% of their contraction time can actually be a while, right? It can be a few million years.
Okay, yeah.
And if you are some poor planet trying to form around one of these stars...
Well, trying to form a planet over here. Do you mind? And just,
It's sterilization all the way through.
Geez.
It's just, yeah.
Yeah.
The bad news is also that the low mass versions of these T Tauri stars actually don't get a lot bigger, a lot better when they get onto the main sequence.
Great, good.
They still stay not as violent, but still pretty violent. And
Started off having a tantrum, and that just carries on through.
yeah.
Excellent.
So if I can make you a little bit sad about James Webb particularly, turns out that we're going to be looking for these planets around really low mass stars that have been through, first of all, this T Tauri phase and may well be still sort of fairly nasty environments. Even if we find the planets, they're not really going to be great to go live on.
Hey, we found a planet. Oh, it's gone. Forget it.
It's just going to be a lump of kind of radiation blasted rock.
Still, I'm sure we'll learn lots.
Yes.
Jeez. That is a bit depressing. Okay.
But anyway, so those are your T Tauris.
Yep.
Then we sort of know a reasonable amount about those because we understand a little bit more of the physics of the way that the magnetism works in these. And I'm not going to pretend I do, but other
Someone
people
does.
do. Yeah.
Other people who are paid money to do that. Yep.
The other ones, the Herbig B, E, and AE. The B and the A actually just tell you what type of star is going to come at the end of this. Okay. So we have a stellar classification scheme where we have a bunch of letters that we assign to different masses of stars especially when they start on the main sequence. So,
And I'm sure that sequence of letters is perfectly rational and makes perfect sense.
it was once upon a time. Well, it's just a historic thing. So when we first started looking at stars and trying to classify them, put them into boxes, we said, okay, these ones all look the same. We'll call that box A. These ones look the same. We'll call that box B, etc.
How'd that work out?
Well, yeah. When we didn't understand the physics of what we were doing, we were just putting stars in boxes.
Yep. Cats and dogs look the same. Put them in a box. The same thing.
Yeah. So, and I mean, there was a lot more for, we're talking about 150 years ago that this was happening.
You can forgive them.
When we first started doing, or even 100 years ago when we first started doing spectroscopy. But since then, we've actually figured out, oh, right, that's what that box means. That's what that one is. This box is hotter than this box. So if you range the boxes back in order from the hottest to the coolest, then you get O, B, A, F, G, K, M.
Well done. Well done, everyone.
And some of them had to be added a bit later, as you can probably guess from the O and the M.
But still, 100 years ago, well done for doing anything at all, I think.
Yeah.
So, yeah.
So our sun sits at the G. So the T Tauri stars that we talked about are going to be basically making the F, the Gs, the Ks, and the Ms, the cooler sort of end. And it's these Herbig ones that are going to be making the Bs and the As. The Os just don't even bother.
Right.
they just skip this phase.
Right.
So that's where the B and the A comes from.
Okay,
anyway.
fair enough.
So yeah, now I had a look into these, and yeah, we don't know really as much about these stars as we do about the T Tauri stars. I think it's fair to say. We have a sense that they're powered by not quite the same magnetic accretion process that the T Tauri stars are, but it's unclear exactly what then that process should be.
Is part of the problem that because they're bigger, this phase goes faster? The bigger you are, the faster it goes, and so you've got even less chance of spotting any of these doing this thing.
Yeah, we only seem to have a small handful of these kind of objects to study. They seem to be less variable in terms of their brightness.
Okay.
Don't know why, but yeah, they're not quite as nasty. They've got hotter disks because they're hotter stars.
Right. Because they're bigger.
Yeah. But apart from that, they're a bit less magnetic maybe, but
They're not chucking as big a tanty, but they're still a bit violent.
So if I was going to put my, planet, choose which one I'm going to stick.
If you could. You choose one of these.
I think I'd choose, one of these. I mean, doesn't mean the star's going to be nice for the rest of its life.
No, but at least for a bit of a breather. You go, look, well, just give us a second, all right? Can you just stop? Yeah.
So maybe these are just the calmer versions. Bigger, calmer.
They're the ones who are lying on their backs in the corner of the nursery, having a little giggle and looking at the bright lights above them. Yeah.
So, but that's about all I sort of dug out about these stars, to be honest. But
that's it. So to recap then, right? We've gone from the building blocks, which is the what was it? The interstellar clouds? Is that what they were called?
Yep.
Interstellar clouds. We got gas and dust. Starts to collapse down. We get to the proto-stars. proto-star stage, which is where nuclear stuff, fusion stuff starts turning on, but that's not enough. That's not going to get you there. You got to keep going. And if you're big enough, then you can become your pre-main sequence star. And if that can keep going, like, does everything that forms a pre-main sequence star go on to become a main sequence star?
Yes, it sounds. Yeah, I think
by
so.
definition.
Yeah,
right.
Pretty
if you've
much.
made it that far, then we just got to wait.
Yes,
got to wait,
yes.
and you'll get there. It's like you've been born and you're a child, but you're not yet an adult.
Yeah.
So that's your child phase. Okay, and then finally we get to congratulations, you've graduated to main sequence. Well done.
Yeah, and you could have gone there through two different routes. You could have had the personality of a T Tauri star, which I kind of imagine is just like constant screaming and tantrums for 18 years.
Yeah, we've all met those kids.
Or you just might be kind of, not, I guess, placid all the time, but at least only occasional tantrums and screaming as a Herbig star. And if you're really massive, I don't know, I don't have an analogy for that you just you're born an adult. Maybe that happens.
Those are the kids who are sort of born and it's like they almost immediately go into, hello, mother. Hello, father. I'm off to get a job. We've met those kids too. So, are you a child or are you like 28 already? Just a bit too serious. Well,
so
Emily,
I'm hoping for the Herbig, the middle ground.
Somewhere in the middle. Well, we shall see. The nice thing is that you will have a little bit of an in-joke that you are going to be able to share as this child is born and starts to develop and gets older, that you will be able to describe this child in ways which they will not understand for quite some time, but will at least give you a bit of a chuckle to get through the tantrums that are inevitably going to come your way.
Yeah, they just better not be born at 8 solar masses.
Oh, hope not for your sake. Well, thank you, Emily, for that tour through the creation and torrid birth sequence of stars. I look forward to finding out which version you end up with for your own child. I hope for your sake you're right and that you get the Herbie star and not the other one. But we'll see. That's an adventure for you for the future. Listeners, if you want to get in touch with us and write in for a suggestion for a future show, if you've got any ideas about other baby universe topics, or indeed anything else that's on your mind that you want to talk about, then you can get in touch with us in a whole bunch of different ways. Emily, name one.
You can get us on Twitter.
Indeed. How?
At SyzygyPod. Now, that's an at symbol, which is like an A with a little curly thing around it.
I think the internet's been around long enough that people are familiar with that
but
one.
I'm not very good at it yet. And then it's SYZYGYPOD.
That bit you're very good at. Nicely done. We are in other places as well.
Yes. In fact, if you actually, I'm going to do this. If you actually just put SyzygyPod into Google, I reckon you'll find the other social media streams pretty quickly.
There can't be many other combinations of those letters in that sequence that leads to anything but us.
Yeah.
If you're on the Facebooks, I don't know if SyzygyPod will get you there, but Syzygy Podcast will. So go and find us on the Facebook, or just head to syzygy.fm, which is our shiny website filled with all sorts of information, all of the past episodes, a contact page where you can send us your details and questions and comments and praise, and there is the great Cosmic Wall of Thanks, where we get to give a shout out to all of the people who have supported us as financial supporters of the show. And if you want to do that, you can do that too. Go over to patreon.com/SyzygyPod. There it is again, where for just the price of a coffee a week, you can help us to keep the electrons pumping through the various websites and things that we do. But of course, the best way to support the show is to tell everyone you know that it exists. Go and find the astronomy nerd in your life and say, have you listened to this thing? You really, really should. Help us to rise up through the noise of the podcast universe. Otherwise, we'll be back again next week, all willing. We're sort of into that phase now, Emily, where I don't know how many shows we've got left.
There's about a
big
95% chance we'll still be here next week.
All right, I'm going to go with those odds. Any idea what the next one should be then? If we've just done Baby Universe, Baby First Stars, Baby Galaxies, Baby Modern Stars, what's next?
I have an idea, but I'm going to keep it for secret. Going to keep some things a surprise, you see.
Okay. Tune in next week to find out what the next baby-themed podcast is. Emily, I will see you in a week.
See you later.
Bye, everybody. Do you know, I've just thought, the life cycle of stars, just talking that one through. They're born and then they go through that middle age part of just being a star. It's kind of like where I feel like I am now, except I'm not much of a star. But then the end part, which is either they just fade away or they explode. And I'm kind of thinking, if you're going to go out, like, I wouldn't mind. I think that would be quite fun.
All of the endings are pretty sad when you get down to it, though.
Yeah, but I mean, what's sadder? Just sort of quietly going out and drifting away.
But the planetary nebula from A Quiet Death, I actually really like planetary nebulae.
I thought planetary nebulae...
They're not as spectacular in a single bang as this.
I still think going supernova at the end of your life, though, that'd be fun.
It's very rock star.
It's very rock star.
Live fast, die young, and have a beautiful corpse.
And blow up the hotel room. Yeah.